Okay, so in this video we're going to talk about data clouds, directional variance, data ellipse, sometimes called covariance ellipse, and positive definiteness. And these are all concepts that can help you better characterize and understand your data. Right. Now, data can be represented using a scatter plot. So I'll refer to this as a data cloud. So here we have two variable data, and each point here represents a row of your data table or data matrix. So the first variable is on the x-axis, the second variable is on the y-axis. Right. And you can see this shape. Now, of course, different data is going to have different shapes, but this shows the kind of a linear relationship between the two variables. Now, I talked about data standardization. So the first step in data standardization is to subtract the mean. And you can see that the mean of this data cloud is not at 0, 0. Now, mean is basically the point in the center. And in order to standardize the data, first we need to move the mean to 0, 0. And we do that by subtracting the mean. We end up with something like this. But you still see the extent of the two different variable directions is different. Right? The extent in the x direction, in this variable, whatever it is -4 to 4. The extent here is something like -7 to 7. All right? So the second step of standardization is to divide by the variance. And that will make the variance be 1 in both of these directions. So that's what you end up here. You have this standardized data cloud, and you can see the extent is the same in both directions. Now notice that the variation along this direction is quite a bit larger than the variation along this direction. And that's very interesting. That tells us a lot about the data. The variance of the data is different in different directions. The variance in this direction is much less than 1. The variance in this direction would be more than 1. So if we can identify the directions of large variance, then we can accurately describe data points in terms of the projection of the data onto those directions. Okay? So let me explain this statement. If we can identify the directions of large variance, okay, so a direction of large variance would be this direction here. So if we can identify these directions of large variance, then if I take any data point and I consider the projection of that data point onto my line of large variance, in fact, this projection is very, very close to the actual data point. So just knowing the projection of my data point onto the direction of large variance tells me a lot about my data. This is called dimensionality reduction. And it's a very important aspect of the analysis of higher dimensional data. Here I only have 2 dimensions, so it's not really apparent what the advantage is. But suppose I have data with 1,000 variables. I want to find the directions where there's a lot of variance, and then I just need to know the behavior of the data along those directions, and that will tell me a lot about the behavior of my data. Now, what does this direction correspond to? Well, if this variable is v1 and this variable is v2, this line here corresponds to a data direction vector, which would be, it's going to be A times a vector E in the v1 direction. This would be a unit vector in the v1 direction plus B times a unit vector in the v2 direction. Okay, so this is a data direction. Okay, now how would you compute the projection of your data onto this data direction? I think that's what I have here. Okay, well, hold that thought and we'll get there. All right, so what we want to do is be able to calculate the variance of the data in different directions. This is what we want to do. All right. Now here is where outer product really shines, and it gives us a very simple way of seeing how to compute this variance. Right. Now, we talked about the correlation matrix. If you need to review the last video, that's fine. Okay. Now, if I have m variables, then this is going to be a m by m matrix. And if there are n data rows, this is going to be the sum of n outer product matrices, right? The size of the outer product matrix depends on the variables. The number of terms in the sum is the number of data rows. Okay. There's an outer product matrix for each sample, vector, row vector. Sometimes this is called a feature vector. Okay. So we have n total outer products summed together. Let's see what happens with each one of these outer products. So just take one. Take a sample one. Okay. Take any unit row vector. Okay, so this unit row vector is going to correspond to the data direction that I had up here. So take any vector in this variable space. Okay, here I have two variables, it's two-dimensional. If I have n variables, it's going to be n-dimensional. I'll have an n-dimensional unit vector. All right, so let me take that unit vector and I'm going to multiply this matrix, xj transpose xj. Remember, the correlation matrix is a sum of terms like this. So I'm going to multiply this one term on the left by u and on the right by the transpose of u. Let's see how that works out mathematically. Right? So here I have my expression. I'm multiplying on the left by u, on the right by u transpose. Right? Then what do I do? Remember that this outer product matrix looks like this. It's the product of a column vector here. Here, let me switch back so you can see what I'm doing. This should be t. Okay. All right. So it's the product of this column vector here times this row vector here. But I'm multiplying on the left by a row vector and on the right by a column vector. Now I can reassociate the multiplication. And I'll group the first two together and I'll group the second two together. Right? So I'm grouping those together. Right? Now what is this? This is an inner product. Okay? So I've converted an outer product into a sum of two inner products. This is the inner product of this variable vector x with, I'm sorry, this is not a variable vector, this is a data vector, this is a row vector, right? This row vector times this direction. All right? So since I actually have two of them, it doesn't matter which one is first, this is the same inner product. All right? So I have the square of an inner product. All right? So the result is the square of inner product. This inner product is not a correlation because the row vectors are not unit vectors. Remember that I standardized the column vectors. That does not mean the row vectors will be standardized. But this inner product still has a geometrical significance. And the geometrical significance of this inner product is the projection of the row vector xj onto the given unit vector u. All right? So here it says a, but that a, say, would correspond to my xj. So this is my xj vector. Here is my u vector. And projection just means I drop a perpendicular. Okay. And this distance here, which is going to be less than the distance of xj, this distance here is the projection of xj onto u. Okay. Now this is good news because remember what I wanted to find was the direction of the data along this unit direction, right? I want to find the direction of the variance along this direction here. All right, now, so where are we? Where are we? Each outer product, when I multiply on the left by u and on the right by u transpose, I'm going to get the square of an inner product. And that inner product is a projection. It gives the amount of this row vector, the size of this row vector along the particular geometrical direction I'm looking at. Right? So that's just for one row vector. Now I can sum this up over all row vectors. Right? So that's what I'm doing here. Because my covariant correlation matrix is the sum of these outer products. Right? So I simply write the sum of these outer products and I get the sum of these projections. Right? Here I have the sum of squares. So we've seen the sum of squares before. The sum of squares is the variance. Actually, it's n times the variance. So I should say that. This is n times the variance. Right? To get the variance, you have to divide by n. Or if you're getting the sample variance, you divide by n minus 1. But it's proportional to the variance. Right? And that's true as long as these values have mean 0. But we've already standardized the data. So if you standardize the xj data, you're also going to standardize the projections. All right? So what we have here, when we take a unit direction times the correlation matrix times that unit direction transpose, we will get the variance of the standardized data cloud in that direction. Right? So that's telling us how the data is varying in that direction. So if, for instance, if I chose this vector direction here, and I performed this calculation, then that would give me the variance in this direction. If I chose this vector direction here, and I did the calculation, I would get this smaller variance there. All right, so what are we going to do with this? All right. Using this tool, we could trace out the variance in every direction. And if you do that, what you're going to get is what's called a data ellipsoid, or a correlation ellipsoid. So here you have some picture. Here you have your data cloud in 3 dimensions, and then you have an ellipsoid that kind of follows the pattern of the data cloud. Gives me the shape of the data cloud. Now this ellipsoid has principal axes. What do I mean by principal axes? Well, you can see these major directions that basically characterize the ellipse. You have this major axis this way, you have another axis this way, and then there's another axis coming out. And these 3 axes are perpendicular. These are called the principal axes. Okay. The principal axes directions are called principal components, or principal eigenvalues, while the associated directional variances are called the associated principal values or eigenvalues. Right? So this is principal component analysis. This is the source of principal component analysis. You have your data cloud, you can fit the data ellipse, you're finding the principal directions of the data ellipse, and you're finding both the magnitude and the direction. All right? And what you want are the directions with large variance, because that's telling you a lot about your data. If I know the magnitude of the projection of this point onto that principal axis, that major principal axis, that's going to give me a point that's very close to my data. Right? Now, if the ellipsoid is not collapsed in any direction. Now here you can see that this is a robust cloud. It has 3 dimensions. Now suppose this ellipse was collapsed down to a pancake. Right? In that case, I can try to draw a pancake. Okay, suppose all the data was in one plane. All right? Then what about the variance in the direction perpendicular to the plane? Well, the variance would be 0, because there's no variation. All the data is exactly in this plane, so the projection of all these data points is 0. All right, in that case, it's not true that U transpose is always greater than 0. But in general, if you have enough data and it's kind of fuzzed out, you will have this relationship that U transpose is greater than 0 for any unit vector U. In fact, for any vector at all, as long as it's not 0. Okay. So that depends on the properties of C. Okay? And this is called a positive definite property of correlation matrices. And correlation matrices can fail to be positive definite. Sorry. I want a T. Okay, we'll just select this one. Can fail to be positive definite if, first of all, if there's not enough data points. If there's not enough data points, it's not going to fill out enough of the space. And number 2, if there are relationships between variables, right? In this case, all the variables are in the same plane, so there's a strong relationship between the variables. And that's called collinearity. Now, there's a third way this might happen if you have imputation errors, but that's when there's missing data. That's kind of beyond my presentation right now. So let me add a little bit of background that I didn't talk about that much. So far, I've been talking about the correlation ellipse because I standardized my data before I did my analysis. Now, you'll also see in the literature the covariance ellipse. And in this case, you don't standardize the variable vectors. You do subtract the mean, but you don't standardize. Now, if you do this, then the same analysis will give you a covariance matrix and not a correlation matrix. A covariance matrix. And the corresponding ellipsoid is called the covariance ellipsoid. So this covariance matrix plays a very important role in daily analysis, particularly when the data has a multivariate normal distribution. So that's just a teaser to relate this discussion to what you may see in literature. So, quick review. We have the data cloud. We have the variance in different directions. We have a way to compute the variance in different directions using this correlation matrix. The data directions, the variance traces out an ellipsoid in different directions. And the principal axes of the ellipsoid play an important role in characterizing the data. Okay, so thanks for listening.